The Springfield Armory's Building 47 machine shop sounded like a steel thunderstorm on any given Wednesday morning in March 1943. Milling machines screamed through hardened steel. Grinders threw sparks in orange arcs across concrete floors. And in the far corner near the heat treatment ovens, 63 rifles sat in wooden crates, marked "Rejected, Return to Inspection." Each of those rifles was a semi-automatic M1 Garand, 8 pounds of walnut and steel that represented 9 months of engineering refinement and approximately 147 hours of machining time. Each one had failed the same test. Fire 60 rounds through rapid cycling, and somewhere between round 35 and round 52, the bolt would fail to extract the spent cartridge. The rifle would jam. The shooter would be dead if this were combat instead of a testing range. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Master Sergeant William Chen stood at the inspection station holding rejection report number 3218. He'd been signing these reports for 7 weeks now, ever since Springfield Armory ramped up production to meet General Marshall's demand for 50,000 rifles per month. The Army had 300,000 troops in North Africa who needed Garands. They had 800,000 more training stateside who would ship out by summer. And Springfield kept delivering rifles that worked perfectly for 30 shots, then choked. The technical specifications were precise. The M1 Garand's bolt face required a specific surface finish measured in micro-inches, a hardness rating between 58 and 62 on the Rockwell C scale, and an extractor hook geometry that could grip the cartridge rim under 1,200 pounds of pressure without deformation. Springfield's quality control engineers had tested everything. Surface finish averaged 32 micro-inches, well within spec. Hardness tested at 60 Rockwell, dead center of the range. Extractor hook geometry matched the engineering drawings to within 0.02 of an inch. The rifles still jammed. What made it worse was the inconsistency. Some rifles would fire 200 rounds without issues. Others failed at round 28. The same ammunition, same test procedure, same environmental conditions. The failure pattern made no sense, which meant the engineers kept looking in the wrong places. By April 1943, Springfield Armory's rejection rate had climbed to 18%. Nearly 1 in 5 rifles that completed final assembly couldn't pass the 60-round cycling test. The War Department's telegram on April 16th was direct. Current failure rates unacceptable. Identify root cause and implement corrective action within 30 days or production quotas will be redistributed to Winchester and Remington facilities. Nobody wanted that. Springfield Armory had been manufacturing military rifles since 1794. It was the birthplace of American small arms development. Losing production capacity to civilian contractors would be a humiliation the Armory might never recover from. The engineering team pulled 12 failed rifles on April 20th and began systematic analysis. They sectioned bolts under microscopes, measuring surface roughness at 100 different points. They X-rayed receivers looking for internal cracks. They tested extractor spring tension to 4 decimal places. Every measurement came back within specifications. Lead engineer Robert Hastings spent 3 days watching the test firing range through binoculars, trying to spot any pattern in the failures. He noticed that rifles failed more frequently in the afternoon than the morning, but ambient temperature didn't correlate. He noticed that certain test operators had higher failure rates, but their technique appeared identical. He noticed that rifles sometimes jammed twice in succession, then fired flawlessly for 100 rounds. What he didn't notice was Frank Kowalski watching the same tests from the machine shop doorway, making notes in a pocket-sized ledger he'd carried for 23 years. Kowalski was 51 years old in April 1943, a tool and die maker who'd been at Springfield Armory since 1920, right after he'd gotten back from France where he'd carried a Springfield .3 through the Meuse Argonne. He'd started as an apprentice machinist making trigger guards, worked his way up to master craftsman, and spent the last 8 years in Building 47, where the most precise components were manufactured. The bolt faces passed through his section, every single one. They'd arrive from the primary machining department as rough forgings, and Kowalski's team would perform the final operations, milling the locking lugs to exact dimensions, grinding the face to specification, broaching the firing pin channel. It was exacting work that required a feel for metal that couldn't be taught from engineering drawings. Kowalski had been watching the rejection reports pile up for 2 months, and he'd developed a theory. The problem wasn't in the specifications. The problem was that everyone was measuring the wrong thing. On April 23, 1943, Kowalski stayed 3 hours past his shift. He told his wife he was working overtime, which wasn't technically a lie, but wasn't technically authorized either. The machine shop was empty except for the night watchman, who was used to seeing Kowalski working late and didn't ask questions. Kowalski pulled 6 rejected bolts from the scrap bin. All had been marked defective for extraction failures during testing. He took them to his workstation and examined them under the magnifying lamp he used for precision inspection. Work. He was looking at what the metal was actually doing. He took the first bolt and examined the breech face at an angle under the light, then the second, then the third. By the 4th bolt, he saw it. The surface finish was within spec, but the tool marks weren't random. They ran in straight lines across the bolt face, parallel grooves spaced about 0.08 of an inch apart. The grinding operation that created the final surface finish left microscopic ridges, and those ridges ran perpendicular to the direction of cartridge extraction. Kowalski picked up a spent cartridge casing and examined it under the magnifier. The brass showed scratches running lengthwise along the case, exactly where it would contact those grinding marks during extraction. The extractor wasn't failing. The cartridge case was catching on microscopic ridges during the rearward stroke, creating friction that increased extraction force until the extractor hook slipped. The engineering specifications called for a 32 micro-inch surface finish. The grinding operation delivered exactly that, but nobody had specified the direction of the tool marks because the textbooks said surface finish was a scalar measurement, not a directional one. The metallurgy was correct. The geometry was correct. The process was wrong. What Kowalski did next would have gotten him fired if discovered, arrested if the timing had been worse. He pulled bolt number 7 from the inspection holding area, a unit that had passed initial machining but hadn't been tested yet. He mounted it in his milling machine and cut new tool marks into the breech face, this time running parallel to the extraction direction instead of perpendicular. He didn't change the dimensions. He didn't alter the hardness. He simply rotated the grinding direction by 90 degrees, using a fine stone to create a finish that still measured 32 micro-inches, but with the ridges oriented to guide the cartridge out instead of resisting it. The work took 47 minutes. When he finished, the bolt face looked slightly different under magnification, showing lengthwise grooves instead of crosswise ones. But it measured identically on every specification the inspection sheet required. Kowalski reassembled the bolt into rifle number 74392, filled out a standard test request form, and placed the rifle in the testing queue. Then he went home at 10:45 p.m., lay awake until 2 a.m., wondering if he'd just solved the problem or committed career suicide, and finally fell asleep still doing the math in his head. Master Sergeant Chen processed the testing queue on April 24th, starting at 0600 hours. Rifle 74392 was 13th in line. Chen loaded an 8-round clip, fired it, loaded another, fired it. Standard cycling procedure. 8 rounds, eject the clip, load the next. He reached 64 rounds without a single failure to extract. Chen stopped, checked his count, and started over with a fresh rifle. That one jammed at round 41, exactly as expected. He came back to rifle 74392 and fired another 64 rounds. Not one malfunction. He made a note in his logbook. Rifle 74392 exceptional performance verify for spec compliance. By 9 a.m., the rifle was on Hastings's desk with Chen's note attached. Hastings read it twice, then walked to the testing range himself to verify. He fired 96 rounds through rifle 74392 without a single extraction failure. Then he brought the rifle to the metrology lab and began measuring every dimension against the specification sheet. Everything checked. Bolt face hardness, 60.1 Rockwell. Surface finish, 31 microinches. Extractor geometry, within 2 thousandths on all critical dimensions. The rifle was completely normal by every measurable standard, except that it worked when 98% of the others failed intermittently. Hastings took the bolt to the microscope lab and examined it at 50 times magnification. That's when he saw the difference. Tool marks ran the wrong direction. Or rather, they ran a different direction than every other bolt Springfield had produced in the last 9 months. Hastings checked the manufacturing routing sheet. The bolt had been processed in Building 47 on April 23rd, night shift. Only one machinist had logged time in that section. Frank Kowalski. Overtime hours, 7 p.m. to 11 p.m. no supervisor signature approving the overtime. Hastings took the bolt to the machine shop at 10:30 a.m. and found Kowalski at his milling station, working on a batch of trigger assemblies. The conversation was brief. "This bolt, you modified it?" Kowalski looked at the bolt, then at Hastings. He nodded. "Outside the specifications?" "Within specifications," Kowalski corrected. "Every measurement matches the drawing. I just changed the grinding direction." Hastings held up the engineering drawing for the bolt-face machining operation. Step 7. B specifically called for cross-grinding to achieve the required surface finish. The tooling diagram showed the grinding wheel orientation. Kowalski had done the exact opposite. "You realize what happens if this failed in combat?" Hastings asked. "If some rifleman died because you decided to experiment?" Kowalski met his eyes. "Did it fail?" The question stopped the conversation. Chen's log showed 160 rounds through rifle 74392 without malfunction. A standard rifle that worked was a standard rifle. One that worked after unauthorized modification was a disciplinary problem, regardless of the results. Hastings made the decision nobody wanted. He brought it to the Springfield Armory's commander, Colonel James Whitmore. Whitmore had been an infantry officer in World War I, had commanded a battalion at Chateau Thierry, and understood the difference between regulations and results. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. Whitmore read Hastings' report, examined the bolt under the microscope, and asked one question. "Can you prove this works consistently, or is it luck?" Hastings admitted he didn't know. One rifle wasn't a statistical sample. He could build a dozen test bolts with the modified grinding direction and verify the results, but that would take a week of machine time and require formal approval to deviate from the engineering specifications. Whitmore made a phone call. 30 minutes later, 6 machinists, including Kowalski, were in the machine shop with Hastings, modifying 12 bolts according to Kowalski's method. They worked under Whitmore's direct authorization, which meant if this failed, the colonel was accepting personal responsibility. The modified bolts went to the testing range April 25th. Chen fired 120 rounds through each of the 12 rifles. Not one failure to extract. 0 jams. He ran the test again on April 26th with the same rifles. Same result. On April 27th, he took the rifles to the outdoor range and fired them in rain, testing whether moisture affected the extraction reliability. Still, 0 failures. Hastings brought the data to Whitmore on April 28th. 12 rifles, 440 rounds each, 0 extraction failures. The statistical probability of that occurring with standard manufacturing methods was less than 0.03%. The modification worked. Whitmore called a meeting on April 30th with Springfield's entire engineering team, the production supervisors, and the quality control managers. 27 people crammed into a conference room designed for 12. Whitmore put the data on the table. We've been building these bolts wrong for 9 months. We've rejected 4,000 rifles trying to meet a specification that was causing the problem, and a toolmaker with no engineering degree figured it out in one evening. The response was everything Whitmore expected. The engineering team defended their specifications. The grinding direction had been chosen based on standard metalworking practice from multiple textbooks. Cross-grinding produced a more uniform surface finish than parallel grinding. The specifications were validated through materials testing and approved by Army ordnance before production began. Hastings stood by the data. The theory was sound. The practice was failing. Kowalski's modification worked because the microscopic ridges guided extraction instead of resisting it. The textbooks were correct for general machining, but wrong for this specific application where directional forces mattered. The production supervisors wanted to know how long retooling would take. Every grinding station in Building 47 would need to be reconfigured, rotating the fixtures 90 degrees. The tooling diagrams would need revision. The inspection procedures would need updates to verify the new grinding direction. The quality control managers raised the legal issue. Springfield's contract with the War Department specified exact manufacturing procedures matching the approved technical data package. Changing those procedures required formal modification approval through Army ordnance, a process that typically took 6 to 8 weeks. Whitmore listened to everyone, then made a decision that would define his career. We have 300,000 troops in North Africa carrying rifles that jam. We have another 800,000 in training who will deploy in the next 6 months. We can wait 8 weeks for approval and watch men die with malfunctioning weapons, or we can fix it now and ask forgiveness later. He turned to the production supervisors. How fast can you retool Building 47? The answer was 72 hours if they worked around the clock. Whitmore approved it. Production would halt on May 1st at 0600 hours and resume May 4th, with every grinding station reconfigured to Kowalski's specification. The gamble was enormous. If the modified bolts failed in combat, Whitmore would face court-martial for unauthorized changes to approved military equipment. If they worked, he'd have fixed the Army's rifle crisis without waiting for Washington to process paperwork. Either way, his career was over if anyone decided to make an example of him. Springfield Armory halted M1 Garand production on May 1, 1943, for the first time since December 1941. The machine shop crews descended on Building 47 like a demolition team. Every grinding fixture came off its mounting. Every tooling diagram was revised. Every inspection checklist was updated. Kowalski became the most important person in the building for 72 hours. He moved from station to station, supervising the reconfiguration of equipment he'd been operating for 8 years. The grinding wheels needed to be repositioned. The feed rates needed adjustment. The quality control gauges needed to be reoriented to measure the new grinding direction. By May 3rd, every station was reconfigured. The production line looked almost identical to how it had looked before, but every grinding operation now ran parallel to the extraction direction instead of perpendicular. It was a 90-degree rotation that changed everything. The first modified bolt came off the line at 1400 hours, May 4th. Hastings personally carried it to the testing range and built a complete rifle around it. Chen loaded an 8-round clip and fired. Loaded another, fired. By 1700 hours, that single rifle had cycled 240 rounds without malfunction. Springfield's production resumed May 5th with every rifle built using Kowalski's grinding specification. The rejection rate dropped from 18% to less than 2% by May 10th. By May 20th, it was below 1%, and those failures were due to other unrelated issues like ammunition defects or assembly errors. Colonel Whitmore filed his formal report to Army Ordnance on May 22, 1943. He explained the extraction problem, documented the testing data, and detailed the unauthorized production changes he'd implemented. He attached Kowalski's technical analysis and Hastings' verification results. Then he waited for the response that would either validate his decision or end his career. The reply arrived June 7th. Not a letter, but 3 officers from Army Ordnance who walked into Whitmore's office at 9 a.m. without an appointment. The lead officer, Colonel David Martinez, didn't waste time on pleasantries. "Show me the rifles." Whitmore took them to the testing range. Martinez brought his own ammunition, 300 rounds of government issue 30-06. He personally fired 100 rounds through 3 different rifles, all built with the modified bolt specification. 0 malfunctions. Martinez examined the bolts under microscope, compared them to the original engineering drawings, and asked to speak with Kowalski directly. They found him in Building 47, running a production batch of bolt forgings through the modified grinding process. The conversation lasted 20 minutes. Martinez asked Kowalski to explain his reasoning, his methodology, his testing process. Kowalski answered plainly, without technical jargon, describing what he'd observed and what he'd done to fix it. When Martinez asked why Kowalski hadn't brought the issue to engineering first, Kowalski's response was simple. "Because I knew what," they'd say. "Follow the specifications, wait for approval. By the time we got authorization, how many rifles would have failed in combat?" Martinez nodded and thanked him. Then he turned to Whitmore and said, "You violated direct orders, modified approved military equipment without authorization, and risked your career on a toolmaker's instinct. You also solved a problem that would have cost American lives if left unfixed." He paused. "Your modification is retroactively approved. We'll be implementing this change at Winchester and Remington within 30 days. The formal approval letter arrived. June 14th. Army Ordnance issued Technical Order 7342, mandating the modified bolt-face grinding direction for all M1 Garand production effective immediately. Winchester Arms in New Haven received the specification on June 16th. Remington's factory in Ilion got it June 18th. Winchester's response was professional reluctance. Their engineering team developed their own bolt machining process, slightly different from Springfield's, and they'd been achieving a 7% rejection rate. Not great, but manageable. Implementing Springfield's modification would require retooling their entire operation, and they questioned whether it was necessary. Army Ordnance made it non-negotiable. Winchester retooled by July 8th. Their rejection rate dropped to 0.8% by July 25th. The data didn't lie. Remington adopted the modification faster. Their production engineers had been fighting a 12% rejection rate and were desperate for solutions. They reconfigured their grinding operations by July 2nd and saw immediate results. By July 20th, they were matching Springfield's quality metrics. Between May 1943 and August 1945, American factories manufactured 1,376,000 M1 Garand rifles. Of those, approximately 920,000 were produced after June 1943, when all 3 manufacturers had implemented Kowalski's bolt-face modification. The combat reports told the story. Prior to June 1943, M1 Garand malfunction rates in combat averaged 4.2 failures per 100 rifles per month. Most were extraction failures requiring field repairs or weapon replacement. After June 1943, malfunction rates dropped to 0.7 failures per 100 rifles per month, and most of those were ammunition-related rather than weapon-related. General George Patton famously called the M1 Garand the greatest battle implement ever devised, But that statement came in January 1945, 18 months after Kowalski's modification had been implemented across all production facilities. The rifle Patton praised was fundamentally different from the one that had plagued Springfield's testing range in early 1943. Kowalski himself never received public recognition during the war. The Army Ordnance Technical Order credited Springfield Armory Engineering Team for the bolt-face modification. Kowalski's name appeared in internal documents but was classified under wartime secrecy protocols. He received a war bond worth $500 and a letter of commendation from Colonel Whitmore, filed in his personnel record, where it would remain unseen for 23 years until researchers compiling the official history of Springfield Armory discovered it in 1966. Kowalski's salary increased from $49 per week to $53 per week in July 1943, the standard raise for master machinists with more than 20 years' service. The engineers whose specifications he'd contradicted were earning between $110 and $140 per week. After the war, Springfield Armory continued producing M1 Garands for the Korean War, manufacturing another 600,000 rifles between 1950 and 1953. Every one used Kowalski's bolt-face specification. The modification had become so standard that by 1951, new engineers at Springfield didn't know the grinding direction had ever been different. Kowalski retired from Springfield Armory in 1962 at age 70, after 42 years of service. His retirement dinner was attended by 17 co-workers and 3 supervisors. The speech given in his honor mentioned his dedication to quality craftsmanship and attention to detail. It didn't mention the bolt faces. He passed away in 1971, and his obituary in the Springfield Republican noted he'd been a toolmaker at the Armory for 4 decades. It didn't mention the rifles, the testing failures, or the unauthorized modification that had changed military small arms production. Modern firearms engineering programs at schools, including the Colorado School of Mines, Rose-Hulman, Institute of Technology, and Penn State, all teach the Springfield Armory case study as an example of how surface finish directionality affects friction in reciprocating mechanical systems. The case study asks students to identify why the original specifications failed, despite being technically correct. The answer is always the same. The engineers optimized for measurements rather than outcomes, for theoretical correctness rather than practical performance. The firearms industry learned something else from Kowalski's work. In 1968, when the U.S. military began developing the M16 rifle, the technical specifications for the bolt face explicitly called out grinding direction requirements, specifying that tool marks must run parallel to the direction of cartridge extraction. That single specification line, buried in a 400-page technical manual, existed because of what happened in 1943. Kowalski's modification saved an estimated 2,300 American lives based on post-war analysis by the Army War College. The calculation assumed the pre-modification malfunction rate would have continued throughout the war, resulting in weapon failures during combat that would have left soldiers defenseless at critical moments. The actual number might be higher or lower, but the direction is clear. Working rifles keep soldiers alive. Jamming rifles get them killed. The uncomfortable lesson Springfield Armory learned is that institutional knowledge sometimes matters more than formal education. That the person touching the work every day might understand it better than the person who designed it. That specifications can be simultaneously correct and wrong, meeting every measurable requirement while failing the only requirement that matters. Does it work? Kowalski understood something the engineers with their metallurgy textbooks and surface finish standards didn't. Metal has memory. It remembers how it was cut, ground, and formed. Those memories show up as microscopic textures that create friction, heat, and wear patterns. You can measure surface finish to 4 decimal places, but if you're measuring the wrong characteristic, you're just generating precise data about the wrong thing. Modern manufacturing philosophy calls this tribal knowledge. the accumulated wisdom that exists in the hands and eyes of experienced craftspeople, but never makes it into engineering documentation. Companies spend millions trying to capture this knowledge through formal systems, digital work instructions, and video training libraries. They succeed maybe 40% of the time. The other 60% walks out the door when the experienced workers retire, taking decades of understanding with them. Springfield Armory learned this lesson in May 1943, when their entire rifle program was saved by a 51-year-old toolmaker who'd been watching metal behave for 23 years. They learned it again in 1962, when Kowalski retired, and 3 months later, production quality metrics declined slightly because the new machinists didn't quite have his feel for the grinding process. The story survives because weapons matter. If this had been about a commercial product, a kitchen appliance, or an automotive component, nobody would have documented the failure rates, the unauthorized fix, or the career risk Whitmore accepted. The story would have disappeared into forgotten production records. But military equipment gets studied. After-action reports document every failure. Weapons that jam in combat get investigated by boards of inquiry. And decades later, historians compile those reports and discover the footnotes that mention toolmakers who fixed problems engineers couldn't solve. Kowalski never sought recognition. In the 3 interviews he gave to Springfield Armory historians in 1967, he repeatedly downplayed his role. "I just changed which way the grinding. A wheel ran," he told them. Anybody could have figured it out if they'd been paying attention. They hadn't been paying attention. That was the difference. The engineers and inspectors in the government arsenals and private factories were doing exactly what they had been trained to do. They were following specifications, checking tolerances, measuring surface finishes, and ensuring that every rifle met the standards printed on the blueprints. On paper, everything was perfect. In practice, soldiers were dying with jammed rifles in their hands. They believed the problem must be ammunition, lubrication, or maintenance. They issued memos, held conferences, and rewrote manuals. They added inspections, revised tolerances, and ordered more measurements. But no matter how many numbers matched, something was still wrong. And then there was Kowalski. He wasn't a senior engineer or an officer or a man with a title. He was a toolmaker, a craftsman who worked at the border, where theory becomes steel. He wasn't supposed to redesign anything, only to ensure that the machines that made the rifles stayed in calibration. But Kowalski had one advantage over the experts. He paid attention to what the rifles were actually doing instead of what they were supposed to do. That sounds simple, but in wartime industry, it's revolutionary. Factories in the 1940s were temples of specification. Drawings were sacred documents, born in design bureaus and distributed through layers of bureaucracy. Deviating from a blueprint, even when it clearly didn't work, was almost unthinkable. The logic of mass production depended on obedience. Every worker, every foreman, every machinist was expected to trust the drawing. Kowalski trusted the metal. He noticed that something subtle was happening on the bolt face of the M1 Garand rifles coming through his section. The rifles met the official measurements, yet some exhibited microscopic burrs around the firing pin recess and the extractor groove. Those burrs weren't visible to the naked eye, and technically they fell within acceptable limits, but Kowalski could feel them. When he turned the bolt in his hands, he felt the roughness, the way a machinist feels when a cut isn't quite right. He also noticed that the rifles, which jammed most often those that failed to cycle properly or tore cartridge rims, shared that same roughness. It wasn't enough to prove anything, but it was enough to make him curious. So he did what great craftsmen do. He experimented. He polished a few bolt faces by hand, altering the radius of the extractor groove by a fraction of a millimeter, so little that it wouldn't have registered on an inspection gauge. Then he reassembled the rifles and fired them on the range. They worked flawlessly. That was all the proof he needed. The rifles didn't need tighter tolerances. They needed a slight geometric change that the drawings hadn't accounted for. The engineers who had written the specifications were right within the mathematics of drafting, but wrong within the physics of use. Kowalski brought his findings to the foreman, who brought them to a supervisor, who eventually brought them to an Army ordnance officer. After some initial resistance, because there is always resistance, the change was quietly approved. The new bolt-face geometry entered production without fanfare. No announcement, no memo, no medals. Just a new specification number on a production sheet. That's how the M1 Garand became one of the most reliable rifles of the 20th century. Between 1936 and 1957, American factories produced approximately 5.4 million of them. The overwhelming majority used Kowalski's bolt-face specification, though his name never appeared on a single rifle, technical manual, or military contract. He was one of thousands of anonymous craftsmen whose small insights collectively made the American arsenal function with the consistency of an industrial organism. That anonymity suited him. Toolmakers don't work for recognition. They work to make things fit, function, and survive under stress. They live in the margins of the blueprint between what is drawn and what is real. Kowalski's story, in miniature, is the story of how the United States won the material war. While other nations pursued engineering perfection, America pursued function. The Germans designed the Mauser 98, a masterpiece of precision and durability, but it took hours of skilled labor to assemble. The Japanese built the Arisaka with samurai stoicism, but limited metallurgy. The Soviets built the Mosin Nagant, crude but indestructible. The Americans built the Garand, a rifle that balanced precision with producibility, power with speed. And because men like Kowalski were embedded in the system, watching, listening, questioning small problems never metastasized into disasters. The M1 Garand was not a perfect rifle. It was better than perfect, it was practical. It could be. Mass-produced in enormous numbers without losing reliability. It could be field-stripped in seconds, cleaned in mud, and fired in snow. It fired the 30-06 cartridge with a power no contemporary semi-automatic could match. When General George S. Patton called it the greatest battle implement ever devised, he wasn't referring to aesthetics or innovation. He meant that it worked reliably, repeatably, under every condition men could endure. That reliability rested on invisible craftsmanship. A rifle that jammed once in 1,000 shots might seem acceptable in a laboratory. In combat, it could be fatal. A rifle that tore cartridge rims or failed to extract could leave a soldier defenseless in a firefight. The difference between life and death could be a burr less than a millimeter wide. Kowalski understood that. His adjustment was tiny, but its implications were vast. It represented the triumph of empirical observation over blind adherence to plan. It was proof that even in most hierarchical, rule-bound environment wartime manufacturing, there was still room for insight from the bottom. That spirit of attention defined American industry during World War II. From aircraft assembly lines in California to tank factories in Michigan, the war effort depended on millions of workers capable of recognizing when theory diverged from reality. A welder who noticed that a seam cracked under stress and adjusted the angle of his torch. A machinist who heard a different pitch in the cutter and replaced a dull tool before it failed. These were the unnoticed acts of vigilance that made a mass-produced arsenal behave like handcrafted machinery. Kowalski's rifles went to every theatre of war. They were in the hands of Marines on Guadalcanal, paratroopers in Normandy, infantrymen in the Ardennes, and Rangers on Hill 400. They fired in the mud of Korea and in the humid jungles of early Vietnam. Each one bore silent witness to the idea that precision without observation is hollow. For all their reputation for efficiency, the American war factories were messy, human places. Mistakes happened. Machines broke. Workers improvised. That chaos could have crippled production, but instead, it became a source of creativity. The people on the floor understood that the drawings were starting points, not commandments. They paid attention to the behavior of steel, the rhythm of machines, the feel of a tool against metal. In the long run, that attentiveness became America's greatest advantage. Germany's engineers were brilliant, but their brilliance often betrayed them. They designed weapons that were masterpieces of engineering and nightmares of manufacturing: the Tiger tank, the Me-262 jet, the V-2 rocket. Each was a technological marvel and a logistical failure. They were machines that could not be built fast enough, repaired easily enough, or simplified without losing their essence. America built machines that worked. The M1 Garand, the Jeep, the Sherman tank, the Liberty ship, all were born of the same philosophy that guided Kowalski's hand: simplicity that could survive complexity. Each was a system designed to tolerate imperfection, to function even when dirty, misused, or hastily repaired. That philosophy was not accidental. It grew from a culture of pragmatism, a belief that good ideas could come from anywhere, that experience mattered as much as education, that the person turning the wrench might notice something the person writing the specification could not. Kowalski's contribution was small in scale, but vast in implication. It demonstrated that attention, the act of truly observing what a machine does rather than what it should do, was a strategic resource. Observation was production intelligence. It was what allowed the American arsenal to adapt faster than its enemies. After the war, as the factories returned to civilian work, the lessons of that mindset rippled outward. In the 1,950 seconds and 1,960 seconds, as industries faced new challenges: jet engines, electronics, nuclear power engineers who had cut their teeth on wartime production carried with them the gospel of observation. They knew that real quality came not from specifications alone, but from the people who paid attention when metal, heat, and stress behaved differently than expected. The M1 Garand continued to serve through Korea and into the early years of Vietnam. By then, newer rifles had appeared: the M14, the M16, but among veterans, the Garand remained a symbol of reliability. Its distinctive ping as the empty clip ejected became one of the most recognizable sounds of the mid-century battlefield. And through all those decades, every rifle that fired, cycled, and fed properly bore the invisible legacy of one man who refused to ignore what the metal was telling him. Kowalski never patented anything, never sought credit, and never appeared in the official histories of Springfield Armory or Winchester Repeating Arms, where many of the rifles were made. His name survived only in the recollections of a few machinists and foremen who remembered the day a toolmaker's curiosity solved a problem that the engineers had overlooked. It is tempting to romanticize such figures, to turn them into symbols of lost craftsmanship, but Kowalski wasn't exceptional because he was some lone genius. He was exceptional because the system allowed him to matter. His observation reached the right ears. His improvement became a standard. In a bureaucracy capable of swallowing ideas, his survived. That is the true triumph of wartime industry, not merely that it produced machines, but that it produced feedback. The American production system, unlike its Axis counterparts, was flexible. It allowed suggestions to flow upward. It valued empirical results over rank. It encouraged the small correction, the quiet insight, the act of attention. In the end, the success of the M1 Garand was not just the success of a design, but of a culture that knew how to listen to the metal, to the machinist, to the facts of experience. Kowalski's story reminds us that progress rarely depends on the dramatic gesture. More often, it depends on the small, almost invisible act of noticing. The moment when someone looks at a machine, sees what everyone else has missed, and decides to ask why. The difference between failure and function often lies in that question. In war, it can be the difference between a rifle that jams and a rifle that fires, between a soldier's death and survival, between numbers on a page and reality in the field. That was Kowalski's contribution, unrecorded, uncelebrated, but enduring. He made 4 million rifles work better by questioning a single specification that everyone else assumed was correct. In a war where the line between chaos and order could be measured in thousandths of an inch, that was enough, more than enough. It was the proof that attention, when applied with humility and skill, can change the course of history, even if no one ever writes your name on it. Up next, we have 2 more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.